locked in here. We'll count down 5, 4, 3, 2, 1. Correct answer on this one. Good. Any questions on it? All right. Well, let's see. 1, 2, 6 people today. I was guessing 4, so we exceeded my expectations by 50%. So today, what we'll do is we're going to start by looking at reaction types, and then I'm going to demonstrate a few reactions over here. We'll look at double displacement reactions, combustion reactions, and then do a little bit of practice here at the end. So what I'm going to get set up here right now, and this is assuming I can find my safety glasses, which shouldn't be hard to find. They're not on my head. Okay. Here they are. Let's see. There's a reason why I have them brightly colored, because you know, when you get older, you'll find out your parents aren't lying to you if they tell you that your memory goes and everything else. It's true. So what we're going to do on this one, and we can write down the reactants that we'll be using. I am going to use, if I can find it here, some copper metal. There we go. Some copper metal. And some aqueous silver nitrate in a bottle like this. And I'm going to cut off a piece of copper wire about yay long. And I'll go ahead and take, oh, I should have cut this a little bit longer. Let me put that in the trash. We'll cut a little bit longer here. I need a little handle. So maybe about this long. We'll cut this off. And then I'm going to take my stylus here, and I'm going to wrap this around the stylus at the end. And then we'll pop this into a test tube. And we'll stand this up like this. There we go. And just so you can get an idea of the color here to begin with, I'm going to go ahead and pour some of the silver nitrate here into the test tube. We'll take a look at how this appears, and right now you can see that this is a colorless, transparent solution. Okay, so we'll set this up here. We'll allow this to react for a bit. We're going to write down the reactants that we're using, and the reactants we're using again are copper metal. So we can say that copper metal reacts with, we had an aqueous solution of silver nitrate to yield and as this is going, we're already seeing that something is happening to this one. That's maybe a little hard to see right now. But as it sits here a little bit longer, I think you should be able to see something's happening with the color in here. Are you seeing color?
Yeah, it's kind of blue.
Kind of blue, yeah. You see the blue in this one? You got it? Okay, and I'll go ahead and pass this around here right now so you can see it a little bit closer. Just be careful. Just hold it here by the edge. Don't drop it. Don't shake the wire or anything, but as this is passing around, take a look at what's happening to the surface of the wire in there. And this particular reaction is yielding two substances. One of the substances that we're forming is copper 2 nitrate, and the other product that we are forming is silver metal. Now the silver 2 nitrate, I'll go ahead and pass it back. The the copper 2 nitrate is something that I can tell is forming because when we talk about copper, remember copper is one of those transition elements And what is true about the charges on transition elements? So it's one of the things that's true. Do you recall? Okay, well, why do I need to call it copper 2?
Because it has all variable charges.
It has variable charges, exactly. So it could be, I know it's copper nitrate. That's something I know as a chemist. We'll look at how we might predict it. But because it has multiple charges, we might ask ourselves, how do we know whether it's copper 1 or copper 2? And again, you aren't supposed to know what all the possible charges are. But here's one of the ways we can tell as chemists. When they have multiple charges, one of the very interesting things about the transition elements is that their compounds are very often colored. In this case, now you can see it's even turning more blue than when you guys saw it originally, and there's more and more silver that's forming on the surface. What I can actually do here is I can take this wire and shake it up a bit, and that silver metal winds up settling down to the bottom here. And I'll let this sit here and it'll keep reacting. But one of the ways that I'm able to tell that it's copper 2 nitrate versus copper 1 nitrate is based on its color. And that again is because the compounds of the transition elements are colored compounds, and depending upon their charge, they have different colors. So if this is something you know, and you would only know it through experience, it's not something you're supposed to memorize or anything, but one to tell the difference because copper 1 compounds tend to be kind of a brownish or yellowish color, and copper 2 compounds tend to be kind of a greenish or bluish color. So I look at this, I see the blue color, and I know now I'm dealing with copper 2 nitrate rather than copper 1 nitrate. So that's one of the clues that chemists use then to help tell us which compound or which charge is present, particularly with those that have multiple charges. Again, as we see this collecting, all I need to do is just shake this up a bit, and I can precipitate more of that silver down here to the bottom. Now, I don't know, have any of you ever been out to New York before, out to Ellis Island, Statue of Liberty? Okay. What color is the Statue of Liberty?
Green.
Green. You know what the Statue of Liberty is made out of? Copper, yeah. So that coating that's on the outside of the Statue of Liberty is actually copper 2. Actually copper 2 oxide. So just like when your car rusts and it forms the rust color on there, kind of the reddish brown color, that's an indication that iron 3 ions are present. When we see the formation of the green coating on the Statue of Liberty, that's telling us that we're dealing with copper 2. And so that's copper 2 oxide that's forming on the outside of the Statue of Liberty. Okay, so that's one of the ways we can use to tell us which products are present. And from here then we can write out a balanced chemical equation. So if we start with copper, copper would be Cu. What is the phase label we'd use for copper to begin with? This is a solid, right? Then we reacted it with silver nitrate. Now to get the formula for silver nitrate, we need to know the formula for the silver ion. Silver is Ag with a charge of?
+2.
Ooh. +1. Yeah, this is one of them that's on our to memorize list because it's actually one of those transition elements. If you don't have your periodic table out, you probably should get your periodic table out. Anybody need a fresh, clean copy of the periodic table? Right. So silver is one of those elements, one of those transition elements that has a fixed charge, and its charge is a single positive charge, and it's actually these 3 elements of the transition elements had a fixed charge. Silver was a single positive. Zinc and cadmium each had a charge of 2+ in compounds. So these are 2+, silver was a single plus. So we have silver nitrate. Nitrate is NO3 with a charge of 1-. So if we have this, Then the chemical formula for silver nitrate is going to be Ag NO3. Phase label will be what's the phase label here? Well, what does the description say? It's going to be aqueous, right? It says it's with an aqueous solution of silver nitrate. To yield copper 2 nitrate, copper 2 nitrate now would be Cu with a charge of 2 plus. So that means copper 2 nitrate is going to be Cu. What will come next? We have NO3. What do we need to do with the nitrate? We need a 2, and what would we need to do around the nitrate ion? Parentheses, and outside the parentheses we'd put in a 2. And then we have silver metal. So this ought to be pretty simple. The symbol for silver is Ag. And what phase are we producing the silver metal in? This here would be a solid phase, so we would put that as an S. And then the copper 2 nitrate, I think we should be able to tell, because the solution's turned blue, the phase label of the copper 2 nitrate is going to be, what are we going to put in here? S, AQ. If it looks like a liquid and we have an ionic compound, the phase label is going to be AQ. It's going to be aqueous. We actually don't deal with too many liquids in here. The one liquid we deal with most of the time is going to be water. But other than that, if we see an ionic compound and it appears a liquid, that means we have dissolved it in water. Now, just out of interest here, since we're doing most of our labs at home, we don't work too much with chemicals that are like this. There's a reason why we store this in a brown bottle. Any idea why we store the silver nitrate in a brown bottle? Yeah. Yeah, it's to protect it from light. Silver nitrate is a photosensitive chemical, and by photosensitive it means it will react with light. It'll decompose, it actually forms silver metal, and if you spill this on your hands, what will happen is that over time it will react with the light and it will start turning darker and darker. So we place it in a brown bottle to prevent its reaction with light. Okay, well at this point then we go ahead and balance this chemical equation. To balance this, what do we need? See, copper is balanced. Silver is balanced. How about the nitrates? How many nitrates on the left? There's 1 here. And over here we have 2. So in front of the silver nitrate we'd put a 2, which means on this side now in front of the silver we'd put a 2. And this would balance the chemical equation. So now, what we're going to do is we're going to look at different reaction types. And to look at different reaction types, let's go ahead and put this in here. We'll put in types of reactions. And there's 5 different types of reactions we are going to classify. The first of these types is going to be a combination or synthesis reaction. And in the combination or synthesis reaction, what we have is 2 or more reactants in a single product. So we might represent it something like this: AB combined together to yield, or A plus B combined together to yield AB. Another reaction type we might look at is what we call a decomposition reaction. A decomposition reaction, we start with a single reactant, which we could label as AB, and a single reactant breaks down to become 2 or more products. A third type that we will deal with is what we call a single replacement reaction or single displacement. These terms are used interchangeably by chemists. Your author calls it single displacement. Most chemists refer to it as single replacement, but they refer to the same thing. In a single displacement reaction, we have two different types. Both of them, however, start with this type of format. It's A plus BC. And in the different scenarios, we could have something like this. And in the first scenario, we will say if A is a metal, we have one scenario, and then we have if A is a non-metal as the second scenario. So in a single displacement, when A is a metal, A and B trade places. A and B trade places. And if A and B trade places, what would the products have for a general formula? One of them would be B, the other would be AC. And of course, we wouldn't leave the arrows in there. This is just reminding us that we have them trade places. And if A is a nonmetal, then A and C will trade places. And if A and C trade places, the possible products would be C plus BA. And that type there is a single displacement or single replacement reaction. Type number 4 is what we call a double displacement reaction. Double displacement. Sometimes it's called a double replacement reaction. And in this one, takes on this format, we'd have AB plus CD. And in this particular one, A and C will trade places. That is, the positive ions trade places. So the positive ions trade places in a double displacement. So if these trade places, the formulas for the products would be C CB plus AD. And just so you know, we could have put it AD plus CB. It doesn't matter because this is a property that's called a commutative property of these equations. It's a commutative property of mathematics. That is, 4 plus 3 is the same as 3 plus 4. So if I had wanted, I could have written the products as AD plus CB, and that would have been the same thing. Okay? And again, that's because 4 plus 3 is the same as 3 plus 4. Chemical equations maintain that same piece. And then the last type that we need to be able to identify is what we call combustion reactions. And combustion means to burn in the presence of oxygen. Means to burn in the presence of oxygen. And if we burn something in the presence of oxygen, that means that if a reactant contains, and let's say that it contains carbon, we say that compounds containing carbon are converted to carbon dioxide. If it contains carbon, it's converted to carbon dioxide. If it contains hydrogen, it is converted to H2O. And if it contains sulfur, it is converted to SO2, sulfur dioxide. And these should all make sense. If we burn something containing carbon, it gets converted to carbon dioxide. If we burn something containing hydrogen, it gets converted to H2O. If we burn something containing sulfur dioxide, it gets converted to SO2. Or if something contains sulfur, it gets converted to sulfur dioxide. So with this in mind then, look at these formats. What we're going to do here is I'm going to pull up the next Socrative quiz. And the next Socrative quiz, at least I thought I was going to. And I'm not, there we go. And the next one will have us classify the chemical reactions. And let's see, how does this one look? Looks like this. So how about we do it like this? We will have this one be open navigation. We'll show your final score, and we'll go ahead and start this one. And you can go through and navigate them, classify them. I think the first one there has 2 possible answers. All the rest of them have 1. If you came in late today, we have a handout. Anybody not get the handout? See if you can classify them by type. When you get to the end, it's going to give you a score. All right, we'll give you about half a minute here, 30 seconds. Okay, let's go through the answers. First one, we have hydrogen reacts with oxygen to produce H2O in the gaseous phase. This one here is classified as, very good, these two here, synthesis and combustion. And this is one of our day 1 demos in here, the explosion of the hydrogen balloon. Next up, we have this one that we just demonstrated right here. We classify this one as single displacement reaction. Our clue on this one is to look at the formula, and copper, this would be a single displacement, because if you look at copper, we see that copper here is by itself, and Copper trades places with which element?
Silver.
With silver, exactly. So remember, we put in copper metal into here, and then we wound up producing some silver metal. So this here is the single displacement reaction. Next up, next up here we go. Lithium sulfate reacts with barium nitrate to form barium sulfate plus lithium nitrate. This one here is a double displacement. Positive ions trade places. Next up, we've got hydrogen peroxide yielding water and O2. This was the genie in the bottle we demonstrated last week. This one here is a decomposition reaction. Why is it not combustion? Combustion means we are reacting with oxygen, not producing oxygen, but that we are reacting with oxygen. And then the last one here, whoops, is that it? I guess it is it. How about that? So any questions on these? All right. So if we go ahead and take a look at our list right here, these are going to be the two types, the last two, are the ones that we are going to be responsible in this course for completing and balancing the equations. So these two here, again, are the ones that you will be responsible for completing and balancing chemical equations. And so we will start with, let's start with double displacement reactions. Double displacement. So completing and balancing double displacement reactions. All right, to do this one, we'll start by doing some demos. Remember that the convention is, for this, is AB plus CD yields. Positive ions trade places. Products are going to become CB plus AD. So to demonstrate these, I brought out a number of different chemicals here today. And the first one we're going to look at is going to be a reaction between calcium chloride and sodium carbonate. So calcium chloride and sodium carbonate. Now, whenever you see an ionic compound as a liquid, we don't put down a phase label of liquid. The phase label we use is aqueous. So about the only one that you really need to know as a liquid is water. Any other compound that we work with, again, that looks like a liquid, if it's an ionic compound that looks like a liquid, that means it is aqueous. If we take these two now and mix them together, get these out here. We'll dump them like this, or one to the other, and we'll see that we get this white cloudiness. And what do we call this when they form the cloudy material? That is a precipitate, right. So we formed what's called a white precipitate. So now we want to write out a balanced chemical equation to show this reaction. We start off something like this. First of all, let's write out the names of the reactants. Again, the two reactants were calcium chloride and sodium carbonate. So now if we write out the reactants here, we need to know the formulas and the charges. Calcium ion is Ca with a charge of how much? 2 plus. Chloride is Cl with a charge of 1 minus. So we have Ca with a 2 plus charge. Chloride is Cl with a single negative charge. This means that the formula for calcium chloride is CaCl2. And again, we saw that it appeared as a liquid, which means its phase label is aqueous. Then we have sodium carbonate. Sodium would be Na with a charge of 1 plus. Carbonate now, we see the ATE suffix. What does it mean if we see ATE on the end? Means it contains the element oxygen. So this is one of your polyatomic ions you need to memorize. Its formula is CO3 with a charge of 2 negative. Therefore, the formula for sodium carbonate would be Na2CO3. Phase label on this is going to be aqueous as well. Because again, if it's an ionic compound that appears as a liquid, like this one does, that tells us it's an aqueous material. Now, to figure out the products, we need to do our double replacement. To do our double replacement now, calcium will now pair up with carbonate, and sodium will pair up with chloride. So again, we do a double replacement. The positive ions trade places. Once they trade places, we have calcium carbonate. What would the formula for calcium carbonate be? CaCO3. And then the other product is sodium chloride. What is the formula for sodium chloride? NaCl. Now, the most common thing that I see students do here is that we see these subscripts of 2 on there. The most common mistake I see is that we put a 2 and a 2 down below, but they don't belong there, and that's because the charge on sodium is 1 plus, charge on chloride is 1 minus. So how do we account for the fact that there's 2 sodiums here and 2 chlorines here? What do we need to do on this side? Put in a 2 as the coefficient. If you put in the subscripts of 2 and 2, then you're writing a new formula for something that doesn't exist. So now that we have these, then the next thing we need to do is to put in phase labels. And this is where your handout will come into play. If you look at your handout, we have a list of solubility rules. And the solubility rules will tell us what the phase labels on here are going to be. So if we look at those phase labels, here we go. We look at the chart, we see it's broken into 2 parts here. We have the part on the top, which we list them as mostly soluble. Part on the bottom where they're listed mostly insoluble. So we look for calcium carbonate, something that would fit into calcium carbonate, and where could we look on here? Do we see anything with either calcium or carbonate in here? Carbonate's down here under the category of mostly insoluble. So if you look under the category of mostly insoluble, of course we then look to see if there's exceptions. If calcium carbonate's an exception, it isn't. So if it's insoluble, what is the phase label we put down for insoluble? That's going to be a solid. And if it's soluble, what do we put in the phase label if it's soluble? Aqueous, right. So S doesn't stand for soluble, S stands for solid. So calcium carbonate then is going to be a solid because it is listed as insoluble. Then we want the phase label here for the sodium chloride. We go ahead and look at the table here. Right away we see sodium up at the top. If it's a compound containing the sodium ion, it is going to be soluble with no exceptions. So we come back to this one here. If it's soluble, the phase label is going to be AQ. And this then is how we write out a balanced chemical equation for this reaction. Any questions on this one here? Any questions? Okay, let's look at, I have two more examples. Oh, and by the way, if we were to do this now, you should be able to see that as this sits here, the solid is beginning to settle down more. You're starting to see this aqueous layer up above. What is the identity of the white solid that is settling here? Calcium carbonate, exactly. The white precipitate is calcium carbonate. If we wanted to isolate the calcium carbonate, what could we do with this stuff? See, now I'm drinking a coffee there this morning. If you make your own coffee, you would have a filter in there. You could pour this through a filter, and where would the calcium carbonate be? In the filter itself. And the stuff that passed through the filter would be sodium chloride. Okay, so when we talk about how do chemists make these things, this is one of the ways we could make something like a calcium carbonate. If we have some sodium carbonate and calcium chloride available, this is one of the ways we could wind up making it. Okay, let's look at another one. The next one, let's write down these formulas. We have iron 3, or the names, iron 3 chloride, that's right, iron 3 chloride. And the other one that I have here is sodium hydroxide. So once again, I'm going to go ahead and mix these together, and we'll watch to see what happens when I do. There's the sodium hydroxide. Here's the iron 3 chloride. Remember when we talked about colored compounds, this is kind of a orangish color. This orange color of iron tells us we're dealing with iron 3. Iron 2 is more of a kind of a greenish color. So now if I take and pour these two, one into the others, we see the formation of a precipitate. And we should now be able to write out a chemical equation for what we just observed. So let's go ahead and write out this chemical equation. First of all, we have iron 3 chloride. This gives us some practice on a nomenclature. Iron 3, what is the formula for the iron 3 ion? Fe with a charge of 3 plus. We don't need to look this up because the Roman numeral tells us the charge. The chloride ion is Cl with a charge of 1 minus. The sodium, we already looked this one up. This is Na with a charge of 1 plus. Hydroxide now, this is one of our to memorize ions. This is a formula of OH with a charge of 1 minus. So now if we put these together, iron 3 chloride. Iron 3 chloride would be Fe Cl3. Phase label is going to be aqueous. Then we have sodium hydroxide. Sodium hydroxide is going to be NaOH. Phase label of the sodium hydroxide is going to be aqueous. Then we do our double replacement. With a double replacement, iron 3 now is going to pair up with the hydroxide. Sodium is going to pair up with the chloride. So we do our double replacement. So we now have iron 3 hydroxide. Iron 3 hydroxide is going to be Fe. Then what do we need? OH. 3. What else do we need besides the 3? We need the parentheses. Remember, if we ever have more than one of a polyatomic ion, We place it in the parentheses and the subscript outside. And then we have sodium chloride. Sodium chloride is going to be NaCl. Now we go back and check phase labels. We go back and check phase labels. We come back to the iron 3 hydroxide. With the iron 3 hydroxide, the solubility table, we would find hydroxide right here under the category of mostly insoluble. We then check to see if iron 3 hydroxide is an exception. It is not an exception. Because it is not an exception, the phase label we'd put in here would be S for insoluble or solid. And then for the sodium chloride, just like we saw up here, because it contains sodium ions, it is going to be soluble, and there are no exceptions. So I put this in here as AQ. Not quite finished yet. What else do we need to do with this? Balance it. So to balance it, we check. We see one iron on each side. How many chlorines here? 3. Over here we have 1. So to balance it, we need to put 3 in front of the NaCl. We now have 3 sodiums. To get 3 sodiums over here, we need to put in 3 in front of the NaOH. How many hydroxides do we have here now? There's 3. And over here we have 3 hydroxides. This then is a balanced chemical equation. Now I know you think you have this down, but I want to look at one more here just in case maybe you don't. So, next one we're going to look at. We are going to combine together some potassium iodide and sodium carbonate. Potassium iodide and sodium carbonate. So we write down the formulas or the names. Potassium iodide and sodium carbonate. We go ahead and pour these out so we can mix them together. Now the Ki here is kind of discolored, but that's okay. It should be transparent. I think it's contaminated with a little bit of I2. But just go ahead and take a look at the colors of these. We see we have 2 transparent solutions. If I mix one into the other, anything happen? No. Okay, so now, this would be an example of no reaction. If we want to write out no reaction, here's how we would go about doing it. First of all, we go back and look up the charges. Potassium, K here, a charge of 1 plus. Iodide is I with a charge of 1 minus. We already looked up sodium as a single positive. We already said carbonate with CO3 with a 2 negative. So then if we want to write out this chemical equation, we'd want the formula for potassium iodide, which is Ki. Its phase label is aqueous. And sodium carbonate now is going to be Na2CO3. Its phase label is going to be aqueous as well. And this yields. Now, because we didn't observe a reaction, what we say is that it is no reaction. And chemists very often abbreviate no reaction simply with NR to tell us that nothing happens, that there is no reaction that takes place. Now, this is something that you need to be able to predict whether or not a reaction occurs. And here's how we can predict whether or not a reaction occurs. First of all, let's say we didn't know that a reaction was going to occur, and then I didn't demonstrate it for you to find out. We could have predicted that it didn't happen because we could have guessed then what the products would have been. If we guessed what the products would have been, potassium would have paired up with the carbonate, sodium would have paired up with the iodide. And if they had gone through this pairing, we could have then written out products of K2CO3 and NaI. And if we had then gone to the solubility tables and checked the solubilities for potassium carbonate, we would have seen that because it contains potassium, it is soluble and there are no exceptions. You say, well, wait a minute, I didn't see potassium there. I looked up carbonate. And carbonate says mostly insoluble. However, if you look at this and look at the exceptions, one of the exceptions is if it contains potassium. So potassium carbonate actually is going to be soluble. So that tells us the phase label here is AQ. And because this contains sodium, and sodium sits here on the list of mostly soluble with no exceptions, the phase label on the sodium iodide is aqueous as well. And so your rule goes something like this. If your equation shows that you're starting with two aqueous ionic compounds, and the products show the two aqueous ionic compounds would form, then there's going to be no reaction. So again, if you start with two aqueous ionic compounds, and the products show the two aqueous ionic compounds would form, then no reaction would take place. In fact, it would be incorrect to even show the products. What you would want to indicate is that no reaction did indeed take place. So that here is our first part of the hour. I'm going to give you a chance to practice here, but any questions that you have on these? All right, here are the three that you're going to practice. We'll do a kind of a semi-working break. I'll give you an extended break here, but it will allow you to work on these. And they are this one here, lithium phosphate, aqueous, reacts with KOH, aqueous, to yield. Skipping down, we'll have magnesium sulfate, aqueous, combines with calcium bromide, aqueous, to yield. And skipping down a bit further, we'll have ammonium phosphate, reacts with barium chloride, aqueous, to yield. All right, here's what you need to do. For each of these three, you need to complete and balance these equations. Complete and balance these equations. Then put in their phase labels. So complete and balance, put in the phase labels. And of these, I'm going to tell you right now, one of the three is no reaction. So the first thing I do is identify which one is no reaction, and then complete and balance the other two. So on an exam, like the one coming up here, I'd say complete and balance these equations. It's up to you to decide or to figure out if it is no reaction. If it is no reaction, write an NR after the arrow. Any questions? All right, we'll give you until 9:10. So that's about 18 minutes here, 9:10. And these three questions, or these three problems, will come up then next on your Socrative app.